Hello everyone. Today we'll talk about the solution to the problem special array 2. In problems like this, where we have some array, some queries about subarrays of that array that we have to answer, we want to avoid going through, for every query, the subarray of that query just starting from scratch, because that typically leads to quadratic algorithms. Because if the queries are for big subarrays, then we have to go through the big subarray for every query. That's no good. There are multiple techniques of dealing with problems like this. One, let's say, family of techniques would be to try to look at queries. Since we're given them all already, we can create an offline algorithm, as it's called. We can rearrange the queries to make sure that answering them becomes easier. For instance, we can sort them by their starting position, so this from of I, or sorted by to of I. There are also some more involved techniques like Mohs algorithm here that just want to minimize the amount of elements that we have to look at through the whole runtime. But there are also other approaches, and this other approach is what I'll be using when solving this problem, and that whole family could be called pre-calculating something, such that we can use those pre-calculated values, focusing on this from and to, and based on those pre-calculated values we can generate an answer quickly without looking at the whole subarray. So the most basic example would be subarray sum. We can calculate prefix sums of the original array, and then when somebody asks us for a sum of some subarray of our array, we can just subtract the prefix sum of the right end and the prefix sum to the left of the left end. And this gives us the sum of the subarray. So we just pre-process something, and then we can answer queries quickly. So what can we pre-process here? We are being told that what we want is we want a pair of adjacent elements to have different parities. And we immediately see that here this is a pretty simple, let's say, monotonic property, in that we have an element, and if that element is a different parity to the next element, then they are together, which means that we can take our array and split it into parts where each part is either a correct array, so every pair of adjacent elements has different parities, or there are breakpoints, and those breakpoints are exactly when two adjacent elements have the same parity. And now to answer a query of from to, we just have to say if the subarray from to is within a single block, within a single special block in our array. So essentially, when we look at it, then we want no breakpoints to be within that query. So we can, let's say, calculate the positions of breakpoints, and maybe for every query we can, I don't know, binary search within the lists of positions to check if any bad position is within our query. But there's also a simpler way, and that simpler way is to note that, as we mentioned from this monotonicity, that we can, for every position, calculate, for instance, the rightmost or leftmost position, such that the subarray from the starting position to the calculated position is special. In other words, we can, for every position, just calculate the longest special subarray in some direction that we choose. And when we're given that, we can just see what is the longest special subarray starting from one of the ends of our queries and compare it with where the other end of the query lies. And we're using this monotonicity property here, in that if we have a special subarray, then every subarray of that special subarray is still special. And this perspective of looking at bad pairs, of looking at breakpoints, is good, because when we use that definition, then of course if we have a big subarray with no breakpoints inside, and a smaller subarray of that big subarray, then there can be no breakpoints inside the smaller subarray. So the solution will look something like this. We'll remember, of course, the length of our nums, and we'll be maintaining an array, which I'm going to call dp, because it can be looked at as dynamic programming, which is the leftmost end of the longest special subarray that ends at our current position. So at first, the leftmost end is the same as the right end, which is just the position that we're in, because every element is in a subarray of length 1, which is special. There can be no breakpoints if there is only one element. And now for every element starting from the first one, we look at the previous one, and they can be together if they are of different parities. So one way of checking for parity is to first extract the least significant bit. So this is 1 if nums of I is odd, 0 if nums of I is even. Do the same with nums of I minus 1 and XOR them together. XOR is exactly the form of exactly the operator that we want to express difference, because it's 1 exactly when 1 is 1 and 1 is 0 of the two operands. And now, of course, if that is true, that means that we can put I and I minus 1 in the same array, which means that we can take the leftmost position that was correct for I minus 1. It's also correct for us, and so it's the best for us, because by the order of calculation or dynamic programming, we know that dp of I minus 1 is already the best, the furthest to the left position for I minus 1. And now for every query, left-right, we check if the left position in the query is not to the left of the leftmost correct position for our value for the right end of the query. So here dp of r is as far to the left as possible to go while maintaining this special property, and we want L to be greater than or equal to that value.